Hello everyone, I'm Jonas and I will present our work on interactive volumetric region growing for MRI scans in WebGL today. Before I get to that, I quickly want to say a couple of words about myself and the other involved authors. My name is Jonas Kordt and I'm a graduate student at the Hasso-Plattner Institute of the University of Potsdam. There, my co-author Paul Brachmann and I are part of a team working on an image segmentation suite for volumetric medical images called Vision. The workflow we present in our paper is part of that work and integrated into Vision. We were supported by Daniel Limberger, who's a PhD student at HBI, and Professor Dr. Christoph Lippert, who's a professor for digital health and machine learning at HBI. While our workflow is universally applicable for any volumetric MRI or CT scan, we focus on brain tumor segmentation. To segment such a brain tumor, one typically looks at an MRI scan one slice at a time. Here we can see one single slice of such a scan. A typical resolution used for brain MRI is 1 voxel per millimeter. This means that for the typical head size, you get around 200 voxels in the X, Y, and Z directions respectively. This particular scan has 155 slices with a resolution of 240 by 240 each. Also, when looking at this example, we can probably all tell that this brain is not healthy. Since brains are usually rather symmetrical, something has to be wrong here. And in fact, the brighter shades of gray in the bottom right corner correspond to the high water content of a brain tumor. In a clinical setting or for studies, it is often necessary to segment out exactly the voxels which are part of the tumor. In clinical practice, for example, tumor segmentations are necessary to conduct risk assessments before brain tumor resection operations. For such risk assessments, one important factor is the minimal distance between the tumor and important motor nerves in the brain. If the tumor is too close to those nerves, it would be very likely that they would get damaged during an operation, which could result in the patient being unable to speak or walk afterwards. But to precisely measure the distance next to the location of the motor nerves, a full tumor segmentation is necessary. Similarly, the tumor segmentation can be used to monitor the tumor volume in a time series, both for large data sets in research studies or for individual patients in a clinic. Segmenting such a tumor looks like an easy task here because we're just seeing one single slice of the scan. In reality, it's a time-consuming and expensive process because a trained radiologist has to go through every single slice of the scan and precisely color the voxels which are part of the tumor. The result is a volumetric segmentation, which, as you can see here, we can also render in 3D in order to give researchers and clinicians a way to see the whole segmentation at once. We use direct volume rendering with ray marching for this view, and in order to run this on any device, including tablets with minimal compatibility issues, we rely on Web3D technology. In particular, we use WebGL with Three.js for both the 2D segmentation editor and this 3D view. However, because creating such volumetric segmentations is a big effort, of course, the ultimate goal is to fully automate this, probably using deep neural networks. The main bottleneck of such neural networks is that they rely on a vast amount of training data which has to be segmented by experts. To streamline this training data segmentation process, semi-automatic segmentation tools are necessary. Different approaches for this exist, but we focus on region growing based approaches. This means that the user places a seed which then grows into a larger region of voxels with similar intensities. However, without knowledge about the structure the user intends to segment, region growing algorithms tend to overgrow the intended region by a large amount. This is why region growing tools in a typical 2D slice-based view are usually limited to segmenting one single slice at a time, enabling the user to judge the correctness of the grown region accurately at a glance. To enable confident and atomic segmentation of a whole 3D volume, we thus use a combination of the standard two-dimensional slice-based rendering and the three-dimensional direct volume rendering. This helps users to recognize large overgrown areas quickly, even for volumetric grown regions. Additionally, we do not force the user to discard the whole grown region in case of an error. Instead, we provide them with a preview that they can interactively tune to scale back how far the region may grow from the seed. This way it is possible to limit the grown region in a way that it cannot escape the intended bounds while still keeping as much as possible of the desired segmentation. The specific workflow of our volumetric region growing tool begins with the user selecting a threshold used for region growing. This threshold controls the maximum difference in intensities between neighboring voxels, which still allows the region to grow. In the second step, the user places the seed. This can be done in both the 2D and the 3D view. In the 2D view, the user can scroll through the different slices and select their seed using their mouse cursor. In the 3D view, the user can click anywhere in the rendered image, and the seed will be placed at the first high opacity intersection of their click with the volume. This works especially well in the cone transfer function shown here. This transfer function works by clipping away a cone from the rendered MRI intensities while not clipping away the rendered segmentations. This way it is possible for the user to look into and place a seed in the middle of the brain while still seeing any pre-existing parts of the segmentation like the teal one shown here. After the seed is placed, the region growing is executed. The grown region is shown as a preview in a distinctive color, in this case the dark blue, to differentiate it from any pre-existing parts of the segmentation. Additionally, a tuning UI panel is opened, giving the user access to a slider that controls how far the region may grow from the seed. This lower image series shows the effect of using that slider from within the 3D view. Next, in the fourth step, the user can then freely switch between the 2D and 3D views while manipulating the slider to control how far the region may grow from the seed. This way it is possible for them to limit the segmentation in a way that it cannot escape the intended bounds. As guidance, different transfer functions can be used. The one shown here renders the prominent edges of the underlying MRI, which can be useful to judge whether the region has escaped the intended bounds. Finally, in the fifth step, the previewed region is merged into the existing segmentation to finish the process. Now that I've explained the workflow, let's get straight into a demo. This is Vision's user interface. From here we can import a scan by simply dropping it into the workspace. In this case we are loading a FLAIR series from the BREDS 2018 dataset. This particular imaging modality already makes the tumor contained in this scan brightly visible. Our task will now be to generate a segmentation mask for it. While previously in Vision we had a 2D smart brush that uses region growing on a single slice, this still forces us to go through potentially many slices and can also lead to segmentations that do not produce objects with smooth surfaces in 3D. These issues can be alleviated at least in part by our 3D region growing workflow. It can be triggered by selecting the 3D Smart Brush tool. We may then choose a fitting region growing threshold. For tumors like this one, we found a value of around 40 for the maximum allowed difference while region growing to be suitable. Next, we can select a seed by clicking on a voxel in the tumor. Vision then performs the 3D region growing and we are presented with a preview of the resulting segmentation. If we are not happy with the seed location, we can click again to find a better one. Currently, this preview shows us the maximum expansion of the grown region. However, using the tuning slider, we can tweak how many steps the region growing should be allowed to grow. It becomes apparent that judging this expansion in 2D alone does not give us the full picture. This is where our direct volume rendering approach comes in. When switching to the 3D view, the whole segmentation can be judged in the context of the original scan. This is facilitated by a transfer function that is based on the underlying scan's gradient. Here we can see that the region overgrew significantly in this particular part of the image. So we can use the tuning slider to dial it back a bit. Once we're happy with it, we can accept the grown segmentation. At this point, it becomes part of an annotation layer that can, for example, be exported for statistical analysis. The power of this layer concept is that we can segment multiple structures on the same scan and visualize them together. Additionally, we can make use of the multimodal imaging to generate more accurate segmentations. Let's import the T1 weighted series for this patient as well and add a new layer to segment out the lateral ventricles, which are these fluid-filled chambers in the center of the scan. Bear in mind, I'm no medical expert, so this segmentation is only going to get as good as my limited anatomical understanding. This time, let's set the seed right from the 3D view. To do this, we can either use a clipping plane tool, or the cone cut transfer function that allows us to see into the scan. As seen previously, we can now tune the allowed growth of the region. To judge this more accurately, we can switch back and forth between the 2D and 3D view. Once we're happy with the shape of the segmentation, we can accept it as before. It is now part of the second annotation layer. As you can see, the segmentations are still not perfect. Due to the way region growing works, they tend to contain small holes where outlier voxels occur. To close these, Vision has a dilate erode tool that can fill small holes by first iteratively dilating a segmentation and then eroding it the same number of times. If further adjustments for even more precise annotations are needed, 2D brushes can now be used for manual touch-up. You may have noticed that the resolution in the 3D view dropped while moving the camera. This happens due to our progressive rendering implementation that ensures smooth frame rates even on consumer-grade hardware. This effect can be pronounced even further if we switch the view quality to low. A second progressive feature of our rendering is that of asynchronous lighting computation. As you can see, with the cone transfer function, the scan appears rather dull and contour-free while moving the camera. However, as soon as we stop, a first local ambient occlusion path is computed in the background and used to re-render the image as soon as it is ready. From there, the ambient occlusion quality is progressively refined. Finally, we want to mention that our workflow also supports virtual reality. And while this might not be suitable as the default mode of working, the enhanced sense of depth it offers, from our experience, helps to better judge the spatial structure of generated segmentations. Now that you've seen our workflow in action, I want to get into some of the implementation details. The region growing algorithm itself is rather simple. We wanted to keep it this simple to minimize potential biases when training a machine learning model with the resulting segmentations. A voxel can become part of the region if one of its 6 neighboring voxels is also part of the region and the intensity difference between the 2 voxels is smaller or equal to the user-defined threshold. Additionally, it's also required that the intensity difference with the initial seed voxel is smaller than 1.5 times the user-defined threshold. This makes sure that the region can't grow too far in case there is a smooth intensity gradient between 2 entirely different areas of the scan. Next, let's take a look at the data flow behind the whole process. The process is initiated by the user selecting a seed voxel. Based on this, an initial segmentation is created containing only that singular voxel, and the seed value is extracted from the underlying scan. In the growing phase, that initial segmentation can then iteratively grow based on the extracted seed value, the underlying scan, and the user-defined threshold. During this iterative growing phase, we use two frame buffers as alternative inputs and outputs to render back and forth between. In each rendering step, the region can grow by one voxel in each direction. The resulting segmentation is visualized as a preview together with the original segmentation and can be interactively tuned by the user to limit how far the region may grow from the seed. To achieve interactive frame rates during this tuning process, we don't only store which voxels are part of the region, but also in which step they became part of the region. As we have 1 byte of space for this and need one value each for the voxels not part of the region and the voxel part of the seed, we end up with 254 region growing steps. During the tuning process, we can then simply threshold against this value instead of having to recompute the whole region growing again. Once the user is happy with the previewed segmentation, it is added to the original segmentation to form the merged segmentation. To allow the user to pick a seed in the 3D view, we use a volumetric picking shader. The result of rendering the whole volume using this shader is shown here on the right. In reality, however, we only need to render the one single pixel that the user actually clicked. This volumetric picking shader performs the same front to back ray marching and color accumulation as the normal volume shader. However, when a small opacity threshold is reached, the ray marching loop is terminated and the current normalized volume coordinates from the ray marching process are rendered into the R, G, and B channels of the output buffer. To indicate that a target was hit, a 1 is rendered into the alpha channel. In case no high opacity is reached during the ray marching process, which means that the user clicked onto the background, a 0 is rendered into the alpha channel. If a target was hit, the rendered normalized volume coordinates are converted into voxel coordinates, which are then used as the seed for region growing. I would now like to invite you to try everything I just explained and show to you yourself. Vision is available online at vision.org and includes the volumetric region growing tool. Sadly, because of data privacy reasons, we cannot share a scan with you that you can simply import. However, if you have a scan of yourself, feel free to import it. Any data that you import will stay on your device and will never be sent to our servers. In case you don't have a scan laying around, you can find open access scans on the internet. With that, I would like to thank you for your attention, and of course we're open to discuss any questions or suggestions that you might have.